The Earth's entire climate is a thermodynamic system powered by a single, massive engine. Orbiting at a distance of 1.5 times 10 to the 11th meters, our planet intercepts a highly specific fraction of that stellar output. At the very top of our atmosphere, this incoming energy, known as solar intensity, averages out to roughly 344 watts per square meter. For any planet to maintain a stable climate over long periods of time, it must exist in radiative equilibrium. The total energy entering the system must exactly equal the energy radiating back out to deep space. The physical rule governing this balance is the Stefan-Boltzmann law. It dictates that the amount of heat a surface radiates is directly proportional to the fourth power of its temperature. Because of this strict mathematical relationship, knowing the exact incoming solar intensity gives us all the variables we need to calculate the Earth's average temperature. Analytical. When we plug that 344 watts per square meter into the Stefan-Boltzmann equation, the result is an equilibrium surface temperature of 255 Kelvin. At 255 Kelvin, or negative 18 degrees Celsius, Earth is a completely frozen, uninhabitable ball of ice. We know from direct observation that Earth's actual average surface temperature is a life-supporting 288 Kelvin. We are missing 33 degrees of heat. The laws of thermodynamics are not broken. Instead, our simple input-output model is missing a critical internal mechanism. To locate that missing heat, we have to crack open the atmosphere and build a two-layer mathematical model. We need to track exactly how energy flows, transforms, and gets trapped before it can escape. We start at the top of the sky, mapping that 344 watts per square meter as it makes contact with the planet. This diagram illustrates the initial solar flux. The first factor we encounter is planetary albedo, the natural reflectivity of the Earth. When incoming sunlight hits bright surfaces like clouds and sea ice, exactly 29% bounces immediately back to space. It plays zero role in heating the climate. That leaves 71% of the total solar energy to successfully penetrate the system. The absorption of that remaining energy is split. The atmosphere directly absorbs 23% through water vapor and ozone, leaving a crucial 48% to pass all the way down to the surface. The vast majority of solar heating does not happen in the air. It happens on the physical ground and the surface of the oceans. To maintain equilibrium and prevent runaway heating, the surface has to constantly get rid of that 48% of incoming solar energy it just absorbed. It sheds this heat upward in three ways. First, liquid water vaporizing into gas carries latent heat away from the ocean. Second, conduction and convection shuttle warm air directly away from the hot ground. But the final, most critical cooling mechanism is the emission of thermal infrared energy. Warmed by the sun, the physical ground acts as a black body, radiating invisible heat energy straight back up. Incoming sunlight easily slices through the clear atmosphere, but this outgoing thermal energy faces a severe physical obstacle. That shift in wavelength, from incoming shortwave visible light to outgoing long-wave thermal infrared, is the exact mechanism that makes the greenhouse effect possible. This energy balance diagram introduces a formal two-layer climate model to account for that outgoing heat, splitting the atmosphere and the surface into distinct interacting zones. The atmosphere isn't empty space. It is packed with trace gases like carbon dioxide and methane that are opaque to infrared energy. At the molecular level, these gases are structurally built to act like sponges, designed to intercept and hold that outgoing heat. This absorption graph shows how they function. Methane and carbon dioxide act as physical oscillators, perfectly resonating with the exact frequencies of Earth's outgoing infrared radiation, represented here by the sharp absorption peak. When these molecules absorb that radiation, they heat up. They must then re-radiate that energy in all directions, including right back down to where it came from. Returning to our two-layer model, we map this as a distinct downward flow, atmospheric backradiation. The surface is now receiving a massive influx of energy from two sources simultaneously. It gets direct solar radiation from the top down and a relentless barrage of back radiation from the atmosphere directly above it. It is this compounded downward flux that mathematically forces the Earth's surface to a stable 288 Kelvin, providing the exact 33 degrees of heat we were missing. A climate forcing is any physical change that destabilizes this carefully balanced two-layer energy budget. In our atmospheric box, the variable E represents emissivity. This is the numerical strength of the greenhouse effect. Increasing the concentration of carbon dioxide physically alters the properties of the atmosphere, raising that emissivity value. Carbon dioxide absorbs specific wavelengths of infrared energy that water vapor normally lets pass through. As CO2 levels rise, it partially closes the atmospheric window that allows heat to escape to space. Earth continues to absorb 71% of incoming solar energy, but the outgoing thermal radiation vector is slightly choked off. Global warming is a measured physical energy imbalance. Right now, over 0.8 joules of excess heat is accumulating in every single square meter of the Earth's system, every second. The Stefan-Boltzmann law strictly dictates how a body sheds excess energy. To increase its outgoing thermal radiation and restore equilibrium with deep space, the Earth's surface has only one physical option: its temperature must rise. We don't feel the full intensity of this imbalance instantly due to the massive thermal inertia of the oceans. The water acts as a planetary heat sink, creating a time lag between the energy imbalance in the atmosphere and the resulting spike in surface temperatures. As the ocean's warming, secondary feedbacks occur. The melting of reflective ice sheets lowers the planet's overall albedo, causing the surface to absorb even more heat. As long as greenhouse gas concentrations continue to alter atmospheric emissivity, the Earth's energy budget remains broken, and the physics of radiative equilibrium dictate that the global average temperature is mathematically locked into rising.